about that. So 6:30 to 9, usual procedure, PSA 21, the basement of PSA. So those who have asked me, how do I do better in this course? I need to improve my grade. You all just focus on the next exam that we're going to take. And so the next exam we're going to take is exam 3. So that's where you put all your energy. It's to doing well on exam 3. Okay, so if you have not emailed me, if you've not replied to my email saying that you cannot in any way make it tomorrow night, please do that. I need to put my list together and give you guys an alternative time. So I sent an email out, reply to that email saying, can't do it. If you want to come later, if you want to come at 7 or 7:30, that's perfectly fine. You don't have to be there at 6:30, okay? All right, so then, of course, if you go to Exam Prep and Solutions, everything at the top now is for the exam. Review outline, vocabulary words, applicable quizzes, and solutions, okay? Yeah.
We never had to worry about those before.
It's for English as their second language. Okay. Other questions?
Oh.
Yeah.
Is there recitation?
Okay, so recitation this week. This is what we'll do. So we'll make recitation a study session. It's an open study session to get ready for the exam. And so that's at what time do those start?
10:30 and 12.
And different rooms?
Yes.
Okay, 10:30 where?
PSA 109.
10:30, so this is tomorrow. 10:30, PSA 109, and noon.
PSA 111.
Okay, study sessions, optional. Anybody can go. So if you have Friday recitation, you want to go, it'll just be group work session. Kirk will be there to facilitate and help you study for the exam. Optional. No recitation Friday. Okay? So, for everybody, do you have an optional study session during the Wednesday recitation time? Yes?
How long when does the study session end?
It's the normal recitation times. These are the normal recitation times, 50 minutes.
Okay.
So there's 10:30, PSA 109, PSA 111, noon. It'll just be like just working in groups, studying together. Okay? He won't have something elaborate planned to present to you. Okay. Questions about exam 3 tomorrow night. Okay? Then where's it? Somewhere. Final exam. The final exam is a week from tonight, May 5th, PSF 166. PSF is between the Palm Walk and Goldwater, the tall building on Tyler Mall. Okay, so PSF is, actually it's very close to where we take our exams, just north of PSA, where we take our exams. Okay, so I'll get same place here in Blackboard. I'll get study resources coming up. So because of the nature of this Tuesday-Thursday setup, and we have this exam in the last week, I don't want to give you a big homework assignment for Thursday, but we have all this very important material this last week of the class that you need practice on. So unfortunately, just the way it works out, we're going to have written homework and web work will be due Tuesday at the time of the final. But that's all very, very important for the final, okay? It's all very, very important for the final. So just you're doing that, you're studying. All this stuff towards the end has a big percentage of the final. Is there a question over there?
Yeah, what time is the final?
7 p.m. Did I not put it there? Yes, 7 p.m. 7 p.m.
To what time does it end?
How long do you need?
How many questions?
It's like a little bit longer than our exams. It's like 35 or 36.
3 days.
Other questions about the final?
Oh, when is the homework on next Tuesday due? Like 8:30 a.m. as usual?
No, I can make it due in the afternoon or something like that. It'll be sometime, yeah. The written you'll bring to the final, and the web work will be sometime near the start of the final.
Okay.
Once it's up, you'll know. Other questions? Okay, so this is the big finale here. Okay, where are we? Where is it? There it is. There we go. Okay. Okay, remember, so we're going to kind of tie together lots and lots of what we've done in the course this week as we come to understand what's the fundamental theorem of calculus. Okay, so we go back to this idea. You know how fast something is changing. You want to know how much of it you have. Okay, so here's this. This is the exact elevation function, or the rate of change of elevation is on the left. Here's our, remember, rate of change. So this is the rate of change of elevation in 100 feet of elevation per mile horizontally, right? So per mile. So this is saying, so here at 1 mile from the border, this is 1, 2, 3, 4, maybe 3.2. So this is the point 1, 3.2. What does it mean? It means at 1 mile from the border, the elevation is 3.2 feet, or 320 feet per mile, upslope, right? Because it's positive. So this is positive 3.2, meaning that right around this place, 1 mile from the border, the inclination of the road is such that for every mile that you would go, you would rise 320 feet. So that's what that rate of change means, 320 feet per mile at 1 mile. And that rate is changing, right? That inclination is changing. So now up here at 2, this is 2, 1. What does that mean? At 2 miles from the border, it's still going uphill, but only at 100 feet per mile. All right, so this is the rate of change of elevation as a function of distance from the border, and then this is our accumulation graph. It's the elevation gain from the border. So as the miles, and so this is all, the rate of change is positive, therefore, what about the accumulation? Rate of change is always positive, so the accumulation is increasing. That's our key fact, right? Our key fact about rate of change and accumulation. If the rate of change is positive, what do we see? We see accumulation is increasing. So we're going uphill this whole way, starting at the border, because the rate of change is always positive. Okay, so now let's start with the practice here. So starting at, say, 0.5 miles from the border, I don't know, until 2 miles from the border, how much does the elevation change? From 0.5 miles from the border until 2 miles from the border. What's the net change in elevation? Can you express that in 2 different ways? See if you can do it. All right? We want to express in 2 different ways the net change in elevation starting a half a mile from the border to 2 miles from the border. Okay, so I'm making this problem up. Ignore this for now. Okay, so that we got exact rate and exact elevation. So exact rate is R, capital R. Exact elevation, capital E. 2 ways to express the change in elevation starting 0.5 miles from the border until 2 miles from the border. Okay, can you tell me one way? Can you tell me one way? Tristan, can you tell me one way to express the net change in elevation from 0.5 to 2 miles from the border? What's that? E of 2, he wants E of 2 minus E of 0.5. Agree?
Yes.
Yep. E of 2 is the elevation change from the border at 2 miles, and then E of 0.5 is the elevation change from the border at 0.5 miles. So if you subtracted, what would that be? If we looked over here on the axis, so there's E of 2, there's E of 0.5. So that length right there on the y-axis would be exactly what I'm talking about. The net change in elevation from 0.5 miles to 0.2 miles, which would be E of 2 minus E of 0.5. Okay, so that's using the E function. Is there a way we can express it using the R function? Is there a way we can use it? Go ahead.
Alright, so there's an initial one, which is at R of 2. And then subtracted from that is R of 0.5.
Okay.
And all this is over 1.5, which is the length of the interval, or delta x.
Okay, so the, you're taking the difference of the rates. That doesn't really work. So what you're finding is kind of the
average.
It's like a constant.
Okay.
Yeah, so that doesn't work. So what I want to get, yeah.
R of 2 minus R of 45.
No, that's just that's just the change in the rate. If you do R of 2 minus R of 0.5, that's just how much the rate changes. I want the total elevation change from 0.5 to 2. Yes, sir?
I get the integral from 0.5 to 2.
Okay.
And that's an Rx dx.
Okay, so that if you weren't thinking that should be familiar now, right? This is what it is, right? What do we need to do? We need to take tiny bits of elevation change. How do we calculate a tiny bit of elevation change? How do we get a delta E? A delta E is calculated by? Oh, please know this. K delta X. So we take a little change in distance from the border, and we consider a constant rate, right? A teeny little constant rate there, and we calculate a little change in elevation by K delta X. And then we do this over and over and over again, starting at 0.5, ending at 2. And then what do we do with all those little bits of elevation change? So we get like a zillion bits of elevation change, starting at 0.5, ending at 2.
Yep.
Add them, and that's what this means. Integral means sum, right? You sum up all these K delta X's, right? This is like K delta X, but a super, super small delta X. And that integral sign means to sum all those up. So we're summing up all the bits of change, starting at 0.5, ending at 2. So these two expressions are equivalent. They both give this net change in elevation starting at 0.5, ending at 2. All right, so now I want you to answer the question that's up there, the example. So now write a function f that gives the exact accumulation of elevation starting from c miles to x miles from the border. So we're going to come along here and say just boom, c. Here's c miles from the border. And now I want to know what's the accumulation starting at c. Now we're going to make it a function to any value x. So what's the accumulation of elevation starting c miles from the border and then ending at any distance from the border x? Go. Can you write that function? Okay, so somebody new. Function f. So we want a function of where we're going to finish up. So what function? We give the net change in elevation starting at C up until any final distance from the border x. Somebody new? Yeah, tell me. How'd she do? Mark's writing it down. Must be good, right? Okay, yeah, that's perfect, right? And it just goes off what we just said. But now it's just we're starting at any arbitrary point C, and then we're making it a function of where we stop. Anyone write it a different way? There's another way to write this function. Yeah, so you can also write it, what? E of x minus E of C.
That's what I was going to say.
But you didn't.
I know, I didn't. You beat me to it.
Okay, so yeah, so we just like we said, we can calculate the net change in elevation two different ways using each function. We can build this function those same two ways, right? We can build it using the integral and the rate function, and we can build it using the elevation function.
Why would you say E?
What?
Why would you say E? Because it's the name of
E is the name of the function.
Okay. That's accumulation.
Okay, so here is that version of it, the first version. Okay, and remember we said this is open form. It reflects process, right? It reflects that process of calculating little bits of change in elevation based on the changing rate and summing all those up. Okay, accumulation is the sum of many bits, each one k delta x, right? So that's this first journey we took. You know how fast something is changing. You want to know how much of it you have. This was our end result of that important journey. That the integral is the sum of many bits of change. K delta x plus k delta x plus k delta x. But just a zillion of those added together, right? Okay, but when we did this back in February and March, we never found a closed form for the integral function. It was always, we just had this open form. We used GC to calculate outputs of this function if we wanted to calculate outputs of this function. We never found a closed form accumulation function at first. Okay? But now we know that that function is also EX minus EC. Sorry, yeah, E of x minus E of C. And so the mastery rules, what? We're given an accumulation function, we could get really fast, we could spit out closed form rate function, right? So mastery now is going the other way. We have the accumulation, and we could get these very quickly. We could get the closed form rate function. Okay, so this is the missing piece of the puzzle in order for us to get a closed form accumulation function. So again, before we had the open form accumulation function only, then we worked on the reverse process, and we found in the reverse process we could get closed form rate functions. And so putting those two things together, we can now start talking about how can we get a closed form accumulation function from rate. Okay? And this is the key to it right here. This principle that we just practiced a second ago, that you can express a net change two different ways, right? You can express the net change as the integral using the rate function, and you can express the net change as the final value of accumulation minus initial value of accumulation. So throughout what we're going to do next, you have to have this image in mind, that we're really just expressing the same value two different ways. This net accumulation, expressing it as open form accumulation and closed form accumulation. Yeah?
All right, so the left side of the integral, that's going to be open form, and the closed is going to be EX minus C.
That's right. Right. Remember what closed form is. It's just like an easy function that we just put lots of inputs in, and it gives us outputs quickly. Open form is the one that reflects process, and we need like technology to solve it for us, right? If we want to get outputs. Okay? All right, so we're putting lots of things together here. We're putting lots of things together. So let's see an example. So here's this general accumulation function both ways, right? The net accumulation from C to X. And here's both forms of that. All right, so if our accumulation function is x squared, then we know that the rate of change function is 2x. Okay, so now, what is this? This is a rate function or an accumulation function? This is an accumulation function based on what rate of change function? There's our rate of change function, right? So if we want to find, so this is accumulation starting at x equals 3 until x, where the rate of change is 2x, okay, or 2t, whatever, so 2 times your input variable. So we want to write this function in closed form. Well, because of the mastery rules, because we know that 2x is the rate of change of x squared, well, then we also know something else. What else do we know? We know that x squared is the accumulation function for the rate of change function 2x. So, based on our net change principle here, we can write the closed form accumulation function for this. Can you do it? Go. See, can you write the closed form accumulation function for this open form accumulation function? So again, we're thinking about the two ways you can represent net change. You can represent it in open form, and also what's the other way we can represent the net change starting at 3 and ending at x? How else can we represent it? Just like we did in the last screen. F of x minus f of 3, right? Where what? Where f is the accumulation function for our rate function 2t. And what is that accumulation function? What is the accumulation function for this rate function? X squared. So therefore, f of x minus x3 is x squared minus 3 squared. Think about the last screen. The last screen, we were two different ways to represent the net change from a starting value of x to a final value of x. Using the rate function, using the accumulation function. They're equal, just like on the last screen. It's no different. Okay? So there it is. So because we know that the derivative of 2x is x squared, that allows us to find a closed form accumulation function when the rate is 2x. So we're using those mastery derivative, all those rules, but now it's backwards, right? So it's like, what function has this as its rate of change? Has this as its derivative? X squared. Yeah.
Is it wrong to use t to find the explanation from
Is it wrong to use? I heard.
t instead of x?
No, it would. So here would be wrong to use x. You can't use x here. So you can't use the same symbol there and there. We talked about that before, because then this will only be the rate at the end. So we need the changing rate from 3 to x.
I don't mean in the rate function, but I mean in the explanation function.
You got to think about the previous screen. You got to have in mind what we did on the previous screen. This question. How do you write in two different ways? Starting at x, ending at c. Starting at x, so this is what this is all about, ending at c. How do you write that amount of accumulation? Using this one, it's the integral from x to c, r of t dt. That gives the net change in elevation from starting at x miles to c miles from the border. But then if we have the elevation function, that's the same as ec minus ex. So there's no t over here. I'm not sure. You want to use t over here? Is that what you're asking? No, so there's nothing. T is our roving. T is the one that changes from x to c. So we can have a changing rate between x and c. That's why we use this different symbol here. But here, all we need is the elevation at the end and the elevation at the beginning. We don't need anything in between, so we don't need t. There is a way to do it. There. Shift down. Sorry. Okay. So let's try another example. Here we go. So here's a function, e to the x cubed. Everyone, what's the rate of change of e to the x cubed? Masters of derivatives. What is the derivative of e to the x cubed? Everyone do it. You should be done. You should have it. Oh, and then that reminds me, there's still a handful of you who have not passed the mastery. You got to get in this week and pass it. Okay, I gave you the times. Sent an email, gave you the times. You got to come pass that. So, derivative of e to the x cubed is e to the x cubed times 3x squared. So now suppose I had this open form accumulation function. I want to accumulate starting at -1 up until x of this rate function, 3t squared e to the t cubed. Can you write that open form accumulation function? Can you write it in closed form? Go, see if you can do it. Write that open form accumulation function in closed form. Okay, so we know that the net change of this, whatever this quantity is, changing at this rate, can also be expressed as the final value of accumulation minus the initial value of accumulation. F of x minus f of -1. But because of our mastery rules, we know what function gives us that rate of change, right? So because of our mastery rules, so we're asking what function has this as its rate of change? What is it? What is f of x? What function has this as its rate of change? E to the x cubed. E to the x cubed. Therefore, the accumulate the open form is e to the x cubed minus e to the -1 cubed. That's right. So let's test it, okay? So let's test this out. We're gonna set up the accumulation function both ways and see that it's the same graph. So f of x was e to the x cubed. Okay, and so we want to graph y equals, there we go. So what was the accumulation function in open form? -1. -1 to x, 3t squared. E to the t to the 3 dt. All right, so let's graph that. Open form or closed form accumulation? Open form accumulation. And so we said in the first part of the course, we never found, we didn't have a closed form accumulation function for this, but now we do. What is it? Y equals? So now we want to write the same function in closed form.
F(x)
Okay? F of?
minus f of x.
Yeah, and so because we've defined f of x as e to the x cubed, we can just, in GC, we can just use function notation to write it. We could also have written e to the x cubed minus e to the negative 1 cubed, like we finished off in the problem when we did it. Let's just do it all both ways. Y equals e to the x cubed negative 1 cubed is negative 1, so we'll just put negative 1. So look, so now we are actually finding, given the rate function, we're actually finding closed form accumulation functions. Okay, let's make sure, so where's our original? So there's the open form, and so both of these should land right on top of it. I'll do blue, we'll make purple. How about? All right, and I'll turn this one off. Same thing, let's do it with it this way. What is negative 1 cubed?
Negative 1. It's negative 1 times negative 1 is negative 1.
I simplified, right? I simplified. Okay, so what is allowing us to find closed form accumulation functions? The mastery rules. But we kind of have to think backwards because we're given the rate and we're saying what function has this as its rate of change, thinking about all those mastery rules, right? So I'm looking at this right here and I'm saying, oh, that's the result of chain rule, where the original function was e to the x cubed. And so that's our accumulation function, will be that with x plugged in minus that with minus 1 plugged in. Okay, more practice. Okay, so here's sine 4x. Find the rate. Should be very easy. Should be done. Okay, what's the rate of change? Yes?
4 times cosine of 4x.
4 cosine 4x. So now here's an open form accumulation function. Accumulate from pi over 3 to any ending value x of this rate function, 4 cosine 4t dt. So I want you to write a closed form accumulation function for that open form. Cody, did you get it?
Sine 4x minus sine 4 pi.
He wants sine 4x minus sine 4 pi over 3. That's it. Or f of x minus f pi over 3, where what? We need the function whose rate of change is 4 cosine 4x. That's what that little f function is. The function whose rate of change is 4 cosine 4x. And you got it. Sine of 4x minus sine 4 pi over 3.
Really quick question.
Yeah.
Up there.
Go ahead.
I got it. Never mind.
Yeah. What's the question?
Never mind. There's an x there.
Okay, here you go. Find the rate of change function. Square root of e to the minus x squared. Find the rate of change function. And let's simplify this to make our life easy. So there's, after you do it, actually see if you can do some simplification here. Okay, so you should be able to simplify it and get that. Yes? If you simplify it, you should be able to get that. If you simplify it, you should be able to get that. I know that what it is. Times. So here I'm doing it outside out. So negative 2x times e to the negative x squared times 1 over 2. Yeah. And if you simplify that, you get this. So the 2's go. And then basically what we have is, so we have the x there. Basically we have a over the square root of a. We have something over the square root of that same something. And what is that? That's just the square root of a. You basically have something over the square root of that same something, which is just like a over square root of a, which is equal to square root of a. So that's why it simplifies to this. So you have the x, the negative x, and then times the square root of e to the minus x squared. Okay, you can work that simplifying out later. Okay, so given this rate function, write an accumulation function. If accumulation starts at negative 2 in two ways, in open form and in closed form. So when an accumulation function, where we're going to start accumulating at negative 2 in open form and in closed form. Okay, open form. Somebody new. G, you want to do it?
So we got to the s. Negative x squared root. Negative t square root of e raised to the negative t squared.
Yep.
dt.
How do you do? Open form. There it is. So here's our rate of change function. We want to start accumulating at negative 2 up until x. Want to keep going? Do you get closed form?
Yeah,
Tell me.
It's equal to f of x minus f of negative 2, which is square root e raised to the negative x squared minus square root e minus 2 squared.
Is it the function g?
Yeah, but what he's written is fine. So it's a yeah. We called it g originally, but
Oh, my bad, g.
it's fine. Yeah. So either way, so what would this f be? It would be. It's kind of like we're starting a new problem here. F is the function whose rate of change is this. We called it g back here, but we could start calling it f now. It's not a big deal that he used f there. Not a big deal at all. Just as long as we know what that f means. F is the function whose rate of change is this. F is the function whose rate of change is this. It's just that we happened to call it g before. Now he's calling it f. No big deal. It's not wrong. It's not wrong.
Let's say it's wrong. I'm just saying we're referring to the function of g.
Right. No, I'm making a point. So I'm making a point that it doesn't have to be g. So you're not locked into using g here. Well, the square comes first. Yes. Yeah, so you're right. It is e to the negative 2. This is what you mean? Yes, thank you. This second term should be this. F of negative 2, the f of negative, or g of negative 2, or f of negative 2, that's this right here. Should be that. Thank you. Okay. So we're going to look at this example a little more closely and so what do I have here? I have the original function. I have the rate function that we found. And then I have, let's see here, what did we do? Is this the one that we wrote? Starting at negative 2 at that rate, which was the given, or the rate function that we found. And so let's see what that looks like. Now we're ready. Okay, now we're ready. So here it is. So this is the accumulation function from negative 2 to any value x, where the rate of change is this rate here, right here that we found. And then to test that, to see if it's right, we found this was the closed form, right? Is this right here the closed form that we just found? So I can make it, say, black, and then it should turn black. Okay, so they agree. So we got the open form, and we got the closed form. So what do you notice about this, the accumulation function here? What do you see about the accumulation function based on this open form that we chose here? I said starting at negative 2 to x. What do you notice observe anything about that accumulation function now that when we graph it? Yeah.
It's concave down.
Okay, and part of it's concave down. So we want to relate this expression to the graph. How do you see anything about the graph that relates to this particular accumulation function that we wanted to graph? Yeah. Okay, so what's happening at negative 2? At negative 2, the accumulation is 0. Why does that make sense? Why does it make sense that at negative 2, the accumulation is 0?
That's where we started.
She said that's where we start accumulating. So if we start accumulating at negative 2, it makes sense that then at negative 2, we don't have anything accumulated yet. And then looking at this, so with this rate of change, according to this rate of change extending from negative 2, then we see that we get this sum amount of total accumulation according to the rate. Okay? So the result of starting accumulating x equals -2 is that the accumulation equals 0 at x equals -2. Should make sense. Okay, so what if I were to so now we want to look at this. I want to start accumulating now at -1. What will the graph What will the accumulation be like if I start accumulating at -1? Talk amongst yourselves. So talk. So I want the accumulation now, same rate function, starting at -1. What will that accumulation function look like compared to this one?
So you're just starting off with 5.
So then, if this accumulation is from -1 to x, then what about the accumulation at -1? 0, right? If we're starting accumulating at -1 by the same thing that we said before, its accumulation should be 0 also, okay? So, how many imagine something like this?
I did not.
Can you see that? So this is a conjecture.
Okay, that's good.
Conjecture, what does that mean? It means maybe. It's what we think. So maybe. That's the idea of a conjecture. Maybe. It's a theory, right? It's like a mini little theory we have. Okay, is it right? So first of all, does the accumulation 0 at -1? Yeah, so that's fine.
Oh, okay, this is derivative 2, right? So it's
No, this is the accumulation function. We're drawing this is the accumulation function with this rate of change. With this rate of change right here. Here's our rate.
but it's not going to be 2.
But I'm making a new accumulation function that starts accumulating at -1. If it starts accumulating at -1, its accumulation better be 0 at -1.
Oh, I thought that was the same one starting at -1 rather than -2. That's why I was confused with that.
That's what it is, right? I mean, isn't that?
No, I mean, like, I thought they would start off at whatever the value of -1 is going to be. This is that particular line, the purple line, like a 0.4 or 0.5 starting line. It says 0. So,
Yeah, but so the point is from before we talked about if the accumulation starts, we start accumulating x equals -1, then the value of accumulation is going to be 0 there. So is our conjecture right? So we got that requirement met, that at -1 accumulation is 0. Is it right? Is this the accumulation function? Yes or no? What's the same about these two accumulation functions, starting at -2 and starting at -1? What's the same about them?
the rate function is the same, it starts at 0.
Okay. It starts at 0. What do you?
Okay,
This one starts at -2. This one starts at -1.
Accumulate starting at 0, I should say, sorry.
Oh, okay, yeah, right. So all right, okay, yeah. All right, they have the same rate function.
It's just the starting value.
It's just the starting value. All right, so let's check that. So how can we visually say here at, how about here at x equals 0.5? I want you to estimate the rate of change of our original one, starting at -2, and then estimate the rate of change of our new function. Go. So at x equals 0.5, estimate the rate of each accumulation function. Go. So maybe this is about, you got to look at the scales on the axis.
Are you doing it first?
If you're going to make this estimate, you want to get a good estimate, you got to use, so, it's so weird. On the screen it looks a lot more. So maybe 0.06. Does my visual make sense? What am I doing? I'm estimating how much the change in y is for a change of x. So the change of x of about 0.2. This is all estimating. It's a change of x of about 0.06, about 0.6 of 1/10. Okay, so about our relative size of the change in y to the change in x is about. The black one. Here's the change. No, the new one. This is the black. The one. 0.3. For a small change in x, what? Y changes about 0.3 as much as the change in x, right? Rate of change. Rate of change. For a small change in x, y changes about 3 times as much, around x equals 0.5. All right. How about our original accumulation function, the pink one? Is its rate, so if our conjecture is correct, these two should have the same rate function. So at 0.5, the rate of change of the pink one should be about the same as 0.3. What do you think? Is it the same? No, why not, Matt?
They're located different points on the graph.
No, we're looking at rate of change. Rate of change right here at 0.5. The rate of change of this one, we calculate as 0.3. What's the rate of change of the pink one?
It's negative.
It's negative. We don't even have to do any numbers, right? We don't have to do any numbers. The new one, the integral starting from -1, it's positive rate of change. The pink one, starting from -2, our original accumulation function, has a negative rate of change. So how about our conjecture? Wrong. Okay? So we had this, so this was right. This idea that it starts accumulating at -1, that's true. But this has a totally different rate function than the purple one. And we just saw one example of that. When it's at 0.5, our original function has a negative rate of change, and then this new conjecture function has a positive rate of change. So not only do we need it to start accumulating at -1, but we need the new graph to have the same rate profile as the purple one. Because, why? Because they're based on this, their accumulation functions based on the same rate. They're just starting accumulating at different places. So we got to start over. So what do we need? We need a function that has the same entire rate profile as the pink one and has this requirement of going through that point, -1, 0. So we're going to throw this one out. So can you come up with what will, if I turn on this function, what will it look like? We need the same rate profile for all x values, and it needs to go through the point -1, 0. Talk. What will it be like? Can you come up with it?
Oh my god. You're so sassy.
So shift, right? Can you do a shift?
Whatever works. You get your final graph has to have the same rate for all x values. It has to have the same rate of change as this one, and it has to go through that point, -1, 0. So what do you think it will be?
Shift of -1.
Shift. I mean,
Oh, right.
we just did a shift to the right. We just saw that was wrong, right?
To the left.
Now you want to go back to the left. Will it have the same rate of change as that?
Yeah, we want that. Oh, but we want to start at -1.
Yeah, so we've already shown that this doesn't work. That doesn't work. Because for every x value, the rate of change is totally different.
Shrink.
How is rate of change represented on the purple graph?
By
By? Yeah, by what?
the rate of change. Oh, from -2 to yes.
By slope, right? Inclination. So we need, at every x value, you need the same inclination. Same rate of change. Same inclination of tangent. And it needs to go through -1. What will accomplish that? Anyone got it?
I think so.
Delta.
Okay, he wants to phase shift it. He wants to shift it down. Let's see, where is...
No, it's like
So, like, let's turn it on. Let's see what it is. Here we go. Ready? For every x value, we need the same rate of change, meaning what? The same slope, the same change in y relative to the change in x. And it needs to go through that point, -1, 0. So the new accumulation function is not the old one shifted to the right, it's the old one shifted down. Because when you shift a graph up and down, you maintain its rate of change, right? The rate of change profile is exactly the same for these two. Let's go back to 0.5. See at 0.5? Imagine the rate of change there. Imagine the rate of change there. The same or different? Same. Okay, imagine the rate of change. So what about at 0? What's the rate of change at 0? 0. Accumulation pauses. Relative local maximum. Same for both. Okay? Rate of change at -1.5. It's a really bad triangle. Another really bad one. Okay? So for every x value, we get the same rate of change, but now we have that condition met where it goes through -1. Okay, and then here's, so there's the closed form. Closed form will be our f of x minus f of -1. The same. So Given a rate function, how many different accumulation functions does it have? Exactly 1 million?
No.
So given a rate of change function, how many accumulation functions does it have? Yeah, so lots and lots and lots, infinite number. Depending, and so like, given the rate of change function, here's the one that starts accumulating at, I can't get it right on. Here's the one that starts accumulating at 0. So this is the integral from 0 to x of that rate function. Okay, so by moving an accumulation function up and down, it maintains its rate function. That's why we have all these different versions depending on where you start accumulating from. You're just going to get different vertical shifts of the same graph. Okay, does it make sense?
Question.
Yeah.
When the graph goes down below the x-axis, meaning like the peak, is
Okay.
below the x-axis, how can we tell?
It
what-
can't. So it can't. So for this rate function, so that's impossible. So if I go, say I go from -5 to 5. So now I'm gonna let the starting point of accumulation change from start from -5 and go to 5. So look what happens. Let's just zoom out on this. So it's the red one. So the red one is I'm changing the starting point of accumulation. Here's -5. There's, oh, it did.
I think it maintains.
What am I doing wrong?
Is it adding it?
Yeah, no, so I don't, it's e to the what? -a squared.
-2.
I have the wrong function here. There we go. Okay. There we go. Now we got it. So I had the wrong accumulation. So I got e to the -a squared. So a is the starting point of accumulation. So it's got to have a starting point. It's got to have a. It's always got to have a 0. See, so it won't ever dip down below. You see that? So then when I get a is positive. So now here's a is positive 1.5. Here's our starting point of accumulation. A is 1.5 right there. Did that answer it? Yeah, so it will never dip below because it's got to have that starting, that's got to have that root, that 0 where it starts accumulating from. Other questions? Yeah.
So the maximum, it can be at 0, but just not below.
Well, this particular function, so that we're just looking at one example, but it has to have, if you're doing an accumulation function, whatever your starting value of accumulation is, you're going to have, that's going to be a 0 on the accumulation graph.
Okay.
So this whole graph could not be below the, it's impossible for the whole thing to be below the x-axis with no zeros.
That's true.
Okay, so let's summarize here. So this is the idea of antiderivative, okay?
Wait, isn't it?
What's that? In order, the accumulation is that it's going to be based on that function that has the rate that we're given. And so that's now antiderivative.
Which is accumulation.
Uh-huh. Okay, so if g is the derivative of f, so g is what you were finding on the mastery test, it's the derivative of f, g is f's rate of change function, then f is called an antiderivative of g. So, mastery test. You were given a function, you found its derivative, right? So now if you were given that rate of change function, we're asking what function has that as its rate of change? What function has that as its rate of change? That's a question of antiderivative. That's a question of antiderivative. You're given a rate, you're saying what function has that rate function? Okay, so given a function, how many derivatives does it have? How many derivatives does it have, given a function? 1. Mastery test, right? Mastery test. Given a rate of change function, how many antiderivatives does it have?
Million infinite.
Remember, think of the open form accumulation. We can start accumulating at any x value that we want. -1 to x, 2 to x, right? So there's many, given a rate function, there's many antiderivatives. Just think of all the vertical shifts that will, of the graphs that will all have the same rate function. So every accumulation function is an antiderivative of its rate of change function. Every accumulation function is an antiderivative of its rate of change function. But every rate of change function has more than one antiderivative. We just saw it in that little exercise that we did with the graphs. Imagine there's lots of graphs that have the same rate function. Okay, so here's a rate function for x cubed. So here is the open form accumulation function, starting at 1 to x of the rate for t cubed. Can you write it in closed form? So write the closed form accumulation function for this open form accumulation function. Can you do it? I want the closed form. I want the closed form accumulation function.
Is that 1 to x?
Yeah, 1 to x is a little small. Yeah. So let's talk about that later. You're changing gears. Work on this. It's the middle of lecture. Work on what we're working on. Okay, so what's different this time? We didn't start out with f of x. You have to figure it out. So now you have a rate function, and so you have to think, what function has this as its rate function?
X4.
Yeah, x to the 4th. So x to the 4th has this as its rate function. So if we start accumulating at 1 up until x, what will the closed form be?
1 to the 4.
X to the 4th minus 1 to the 4th. The net change, right? The net change can be expressed two ways, in open form and in closed form. It's just now, I didn't tell it, we didn't start with, you have to think backwards. You've got this rate function. What function has that as its rate function? Well, x to the 4th. Okay, this one. What's the closed form of this one? X to the 4th minus?
-5 to the 4th.
Is it the same function or a different function?
Oh,
Is this the same closed form accumulation function as this one or different?
it's a different closed form.
It's a different function. This one's -1. This one's minus 625. Totally different functions, but they have the same
Rate of change.
rate of change. Okay, this one. Starting now, accumulate with the same rate function starting at pi. Closed form accumulation is
X to the 4th.
x to the 4th minus. Okay, so let's go back one there. So how can we test to see if this is a correct accumulation function? How can we test it? What can we do? Take the derivative and we ought to get
4x.
the rate of change. So do it. Ready? 4x cubed minus 0. All right, check this one. Rate of change is 4x cubed minus 0. So all of these open form accumulation functions are based on the same rate. So the derivative of each of these should be the same. The rate of change, 4x cubed. Okay, so the improper integral, notice, no limits of integration, right there, that represents all antiderivatives of 4x cubed. That right there represents every antiderivative of 4x cubed. Okay, and what is the form of every antiderivative of 4x cubed? What is it? It looks like this, right? It's x to the fourth minus whatever the start. A, so a to the c to the fourth. Yeah, c to the fourth. But so actually, let's call it a to the fourth.
We go from
And in every case, this minus a to the fourth is just a number, right? It's just a number, 1 to the fourth, negative 5 to the fourth. It's just a value, okay? So that minus a to the fourth in this case is just a constant. So we can write it this plus c. So that plus c is just the same thing as in this case, minus a to the fourth. So in general, that c is minus f of a, where f's rate of change is this one. Well, that summarizes it. Okay, so when there's no limits of integration, when it's empty here, it's empty here, it's empty here, that means every antiderivative of the rate function that you're given. And those all have this form, f of x minus f of a, and you could also write it f of x plus c. Okay, so what I'm going to do is,